So having learned that how to quantize fields and how to obtain relevant quantities out of the quantum fields, now we move on to start coupling atoms with quantum fields which are present in nature, and we will see how their interaction leads to new phenomena in terms of light matter interaction or quantum field matter interaction. So the toy example, I will start with interaction of atoms, quantum mechanical systems, with electromagnetic fields present in the nature. In the background, there is a field which is electromagnetic field, which now will be treated not classically but quantum mechanically as well. So both the systems are quantum system, quantum atom, and quantum fields talking to each other. Let us first write down the equations of motions and relevant Lagrangians, which will give rise to relevant Hamiltonian, which would be useful for studying their interaction. So in terms of electromagnetic field interaction, we can think of a charged particle which is talking to the fields, and we have an equation of motion of the kind which we know from Newtonian or electromagnetic interaction, is that the acceleration generated, at least for non-relativistic particles, is proportional to the forces acting on the charged particle. One component of the force is the electric field force, which talks to the charge of the particle and gives rise to this QE kind of term. And then there is another set of term which is QV cross B, where V is here written as R dot. So this kind of terms, as we have seen, are usually present in the Lorentz force description, which we have considered previously as well. Now, in terms of electromagnetic potentials, electromagnetic 4-vector potential, I can write down the electric field as a gradient of a potential minus del A upon del T, the vector potential's temporal derivative. Remember, in electrostatic, this term would not have been around. In the electrostatic, the del A upon del T term would not have been around, and only the gradient term would have been there. But since we are considering electrodynamic or electromagnetic field theory, the dynamics in electric field has to be set up, which is generated through the dA dt term, which is present over here. Okay, all right. The magnetic field remains as the previous version, which is the curl of a vector potential, which is this. Now we can see that we have overall the equations of motion written in terms of all the vector potentials and the scalar potential as this, where I have a gradient term, then there is a electric field term which is also made up of del A upon del T, and then there is a V cross B term which I have written as R dot term over here, and the magnetic field term which is a curl equation, curl of A. Now this is a vector equation. A vector acceleration is coupled to or is written in terms of vector forces. Now we can have different components of these in terms of 3 acceleration components, which I'm going to call R dot M, R double dot I stands for 1, 2, 3, the 3 components of acceleration. They will be obtained from the x component. For example, I is equal to 1, which is x component of the acceleration, will be obtainable from the x component of the gradient of the scalar potential minus the temporal derivative of the x component of the vector potential del Ax upon del T, plus the x component of the whole q v cross b term. So v cross b is a scalar, is a vector cross product, which in terms of the vector potential becomes r dot, which is v cross curl of A, and the whole vector's x component should be selected in order to communicate it to the x component of the acceleration. This is just a notation wise issue. There is a compactor way of writing this, which is in terms of Levi-Civita tensor, which we have previously discussed as well. So if I have to obtain the x component of the cross product of 2 vectors, suppose this is vector A and this is vector B. If 2 vectors have to be taken a cross product, I can write it in terms of Levi-Civita tensor, epsilon I j k, and if I have to get the ith component over here, I will put that ith component as the first index of the Levi-Civita symbol, and the second or third component j and k will appear with the first vector in the cross product and then the second vector in the cross product. This is the first vector, which is r dot, its index will become j, and the third vector is curl of A, its index will become K. And this is this K which gives rise to this epsilon KLM del LAM. Okay. So now we can see we have two Levi-Civita tensors coming about, epsilon ijk coming from the first cross product which I have written, and then epsilon KLM coming from the second cross product of this. So now you see the K index appears in both of them in upper and lower section. That means it is summed over and repeated. And there is identity about the Levi-Civita tensors one index contraction, epsilon ijk, epsilon KLM, something which has appeared in our cross product. Let me clean it up so that we can see it from clarity. Epsilon ijk, epsilon KLM is equivalent to delta I, the first index here, should be the first index which is not summed over there, L, and the second index should be J and M, delta JM. So I should be L and J should be M, minus I should be M and J should be L, the reverse version. The first index which is not summed over becomes the last index which is not summed over in the second term, and vice versa. So this identity is handy because using this identity we can write down the overall term which is appearing as Rj dot epsilon ijk epsilon klm del lam, as we can subsume the two Levi-Civita tensors in terms of product of Kronecker deltas, delta il delta jm minus delta im delta jl, and you see these will give rise to two terms. First term, this will just replace L with I and J with M with J. So I will have a delta I Aj, and the second Kronecker delta product will do the reverse. The first index of the derivative will be replaced with J from this delta JL, and the last index M will be replaced by I from this delta IM. So therefore I have a delta JAI. So now we have all the things in our hand. We have the first ith component of the acceleration is equal to minus q times these two terms, where this first gradient with respect to ith coordinate, then the temporal derivative of the ith component of the vector potential, and the ith component of the cross product between V and curl of A, which is this term. Okay, so we have all the components of the fourth term which we have written previously, and this is the compact notation of writing the various components of the forces. Okay, so let us go forward and try to ask which Lagrangian gives rise to this kind of force equation. This will be handy because we want to go to the Hamiltonian of the system and therefore quantize the system in the canonical approach. So I just again, like before, propose a Lagrangian which gives rise to this equation of motion. Again, you can ask from where I can write, I do write this Lagrangians. In this course, we are not discussing how to write consistent Lagrangians corresponding to interactions, but anyway, you can see it later on that all the symmetries which we have required so far, which is consistency with Lorentz transformations, will allow for a moderate a Lagrangian of a moderate kind, which would be useful. And the simplest Lagrangian in that setting will be this Lagrangian which we are just discussing as of now. So let us first do it, the analysis, and then we will see its covariant form in the relativistic picture. So the Lagrangian which I am proposing is just the kinetic term, which is the usual, minus the potential term is of a particular nature where I have a q times the potential, q times phi, and then there is a dot product between the velocity and the vector potential, q r dot a. This is the dot product between the velocity and the vector potential. Now let us see what kind of equations of motion it gives rise to. Hopefully it will give rise to the equation of motion which we just saw. First we obtain the conjugate momenta corresponding to the various components of the velocities, the various components of the configuration space variable, which is r. R is like our q. So del L upon del q dot, there are three q's, r1, r2, r3, x, y, z. So with respect to ith position vector, ith component of the position vector, the momentum will be defined as pi. And you take the Lagrangian and obtain the partial derivative with respect to Ri dot. Ri dot is appearing in two terms. First, it is appearing in the kinetic term over here. It is made up of R1 dot square plus R2 dot square plus R3 dot square. So Ri dot is hiding here, as well as in this term where also I have a R1 dot times AX plus R2 dot times AY plus R3 dot times AZ with a minus sign after all. So you can see that overall, if I do the partial derivative of the Lagrangian with respect to Ri dot, then I will get Mri dot from the kinetic term and plus Q times Ai. There is a minus sign here and there is a minus sign afterwards alongside outside as well. Overall there will be a plus. So I will have a Mri dot plus Qai. That would be the conjugate momenta conjugate to Ri. Okay. Now the equation of motion will be obtained from the Euler-Lagrangian equation, which is del T of the momenta. So del T of del L upon del Ri dot. Take the time derivative of this equation over here. The first term will be just the acceleration term, Mri double dot, and then the total derivative of Q times Ai, which becomes Q times del Ai upon dt. This is the total derivative. Therefore, the total derivative can be written in terms of partial derivative with respect to t and then the chain rule, the partial derivative of ai with respect to rj and then drj upon dt, which is written as rj dot. So this would be the first term in the Euler-Lagrangian equation, left hand side term. Right hand side term in the Euler-Lagrangian equation is del L upon del Ri, which again I will search for where is the occurrence of Ri in the Lagrangian. Ri appears in the potential over here, in the scalar potential over here and in the vector potential over here. So there are two terms which contain the information of position. One is the scalar potential and one is the vector potential. So both these terms will undergo the derivative with respect to Ri. So first term I will get del phi upon del Ri and the second term I will get just R dot times del A upon del Ri. I have written the dot product between velocity vector and the A vector as Rj dot times Aj, and J is summed over, and the partial derivative with respect to Ri is just going to hit the Aj part of it. Remember, this J and upper J and lower J are appearing in the diagonal and they are summed over. So now both the terms of the Euler-Lagrangian equation is obtainable. Now we can equate this to the equation over here, del L upon del Ri. And overall, what I can do, I can take the extra term from the left hand side, which is the Q times del Ai upon del T plus del A R del Rj times Rj dot to the right hand side. So I bring it on the right hand side. So I see there are certain kind of structure which appears in the Lagrangian equation of motion. Right hand side already had a del phi upon del Ri term, and a minus q del ai upon del t terms comes from the left hand side. So this term over here comes to the right hand side and becomes a minus q del ai upon del t, which is fine. On the right hand side already I had a plus q, minus here, plus q times rj dot and del aj del ri. So rj dot del aj del ri, which was already there on the right hand side. Now the remaining last term which is present in the left hand side would be just transported on the right hand side to become minus of q rj dot del ai del rj. This is the last term which has appeared. Now compare the equation of motion we just wrote above. This is the same equation of motion which we discussed for a charged particles motion. So you see we have obtained a Lagrangian which gives rise to our usual familiar electromagnetic field interaction of a charged particle. So this Lagrangian will be useful as we discussed, because we can write down the Hamiltonian of the system from this Lagrangian. Again, how do I do that? I have all the three momenta px, py, pz, which is del L upon del x dot, del L upon del y dot, del L upon del z dot, which is just elaborate form of del L upon del Ri dot, which I had written previously. We know it will be of the structure MRI dot plus QAI, that means MX dot plus QAX, MY dot plus QAY plus MJ dot plus QAZ. This would be the three momenta. And the Hamiltonian which can be obtainable from this momenta would be summation over Pi and Ri dot minus L, Px x dot plus Py y dot plus Pz z dot minus L. And at the end of the day, all the dots have to be converted into momenta. So this is what we do. Pi, I have converted all the dots, which is x dot. X dot is nothing but Px minus Qax divided by m, that is x dot. So Px dot, Px times x dot will be Px times Px minus Qax upon m. Similarly, Py times y dot will be Py times Py minus Qay divided by m, and Pz times z dot will be Pz times Pz minus Qaz divided by m. Collectively, I am writing as Pi times Pi minus Qai divided by m and summation over I. This is the representation of this term, and the Lagrangian also had a dot in it. Remember, Lagrangian had two places where dots were appearing. One was in the kinetic term and one was in the potential term. So that's what I do. All the dots I replace with Pi minus Qai upon m. So this becomes, the first term over here becomes the square of this, because this was r dot square, and the second term over here was just r dot times ai. So this r dot is just q times Pi minus Qai upon m times ai. Okay, so let me clean it up once we have understood where are the terms coming from. Now you can see the Hamiltonian which we were writing has a very neat structure. Actually, you can collect all the terms which are Pi minus Qai common, and you will see that ultimately this whole expansion is nothing but Pi minus Qai whole square divided by twice m and sum over I plus Q phi. So this Q phi, which is appearing as a solitary term independent of P, remains like it is, and all the other Pi dependent terms make up for a perfect square, for a perfect square kind of term which is available here. Okay, so this is how the Hamiltonian of a non-relativistic system talking to electromagnetic field is written about. Okay, now what we can do, we can just open the Hamiltonian up, the whole square term which is appearing over here, and then try to see if I quantize both the quantum particle. That means I will quantize the Pi which is belonging to the quantum particle, position xi, yi, zi which belongs to the quantum particle, and the electromagnetic field, that means the potentials ai and phi, both of them belong to the quantum field. If I quantize all of them, what happens to the whole Hamiltonian? So let us open the whole term. I have a first term of the Hamiltonian is, let me clean it up. First term of the Hamiltonian is Pi minus Qai whole square upon 2m. Open it up, you will get a P square by 2m plus Q square A square by 2m, which is the two square terms, and then there is cross term Pi minus P twice of Pi Qai divided by 2m, but that is the classical square. If they are quantum operators, two times of term will come out, one with A dot P and other is P dot A. Unless these two things commute, we do not know how to write them as a common term. So I will keep it like that, A dot P plus P dot A. As we had discussed previously as well, in quantum mechanical systems, let us not jumble the order. Let us keep the order in which they appear. So this square term, which we traditionally remember from the classical expression of x plus y whole square is x square plus 2xy plus y square, is actually x square plus xy plus yx plus y square. So therefore this xy plus yx in our context would be written as A dot P plus P dot A, and these two things may not necessarily be the same thing. So therefore I will keep it as they are. At this stage, If I say that the electromagnetic field which is set up in the background is very weak, that means potentials are not very large, then the A square term, which is appearing as the last term over here, can be thought to be very, very weak. If I enforce that A is very weak, the vector potential and the scalar potential themselves are very weak, that means their squared versions, their squared version would be further weaker. So therefore, I should be legitimately be eligible to drop off this term from the full Hamiltonian, saying that it will just cause insignificant changes into our description. Leading order changes from the quantumness of electric field and the quantum particle both, electromagnetic field and quantum particle both, is captured by this term, q by 2m, a dot p plus p dot a, where a and p both are operators. So this I'm going to define as a leading order perturbation Hamiltonian. This would be the second order perturbation Hamiltonian, but right now we are just contained with a leading order perturbation theory. So I would not worry with much of a cause concern, because this indeed would cause some trouble, but not at the leading order. It will be very subdominant kind of correction this can bring about. And next, I know how to write the quantum operators P for quantum particles. Its representation is iota h del del x in position space. And I know how to write the operators A over here in quantum electrodynamics, which we have just done. We know how to write down the vector potential. Vector potential are written in terms of operators, which come with not only the knowledge of the momentum, but also with the knowledge of the polarization vector A lambda. And there is a vectorial character to the field. A field is a vector field, so therefore there is a basis E lambda which accompanies the field description along. So this would be the full description up to leading order of a quantum particle talking to electromagnetic field. Now, for a special case, we can think of electromagnetic field which is monochromatic in light. That means I'm artificially going to impose a condition. This is not very natural condition, but let us just for sake of discussion, if I impose that this A lambda P operator is just present only for a particular momenta, P naught. Suppose there is no field modes excited or anything at any other momenta apart from P naught, I can write down this A lambda P to be made up only with one momenta, P naught. So therefore, in this integration, if I write down this A lambda P as A lambda naught P naught, a new operator, a tilde operator, A lambda tilde. See, there is a tilde in the denominator, in the below the A symbol, so that they become dimensionally different, and delta function takes care of the game that it is only present at one momenta, and this delta function, Kronecker delta, just identifies which direction it is polarized along. So this is a very very artificial kind of arrangement I'm just discussing about, that only in a particular direction the vector potential is pointing. That means electric field and magnetic fields direction, I know which direction we are talking about, and I want to say that I am talking about a monochromatic light. That means only one wavelength is present, that this integration will be replaced by just one number. In this whole integration, only one term survives with momenta P naught and with polarization lambda naught. Okay, and in this case, if that is the case, then the term which is accompanying it along, e to the power I p dot x, which can be broken in terms of a space and time part, e times I e to the power I k dot x and e to the power minus I omega t, which is just decomposition of this four dimensional inner product. And then what I can impose, suppose my momenta P naught, which I had, the only momenta which is present in the field, is very big wavelength. That means k is very small. If k is very small, then e to the power I k x can be approximated as 1 plus iota k dot x. This expansion of exponential function gives rise to 1 plus iota k dot x plus iota k dot x whole square by 2, but higher order terms will become higher powers of k, and k is supposed to be very small, so I can truncate the series up to leading order, which is called the dipole approximation. Actually, the zeroth order dipole approximation is just dropping k dot x altogether, but if you wanted to have some information of wavelength into the game, I will just replace this e to the power ik dot x with 1 plus iota k dot x. And k belongs to the same wavelength where the integration has survived. So it will become k naught dot x. So therefore, e to the power ip dot x was appearing, which will become 1 plus iota k naught dot x, and e to the power minus I minus I times omega naught t. The omega also is at the same frequency. Okay, and then E lambda naught, one polarization survives, dotted with the P dot product of P is coming from here. So the first term which is appearing over here becomes this whole operator in the dipole approximation. The first whole term is the A dot P term. Similarly, if I write down the P dot A term, this time the dot product, the P will appear on the left as it is present over here, and the A will appear on the right hand side, and it I have to write in terms of this thing. I have to write in terms of the A and A daggers again. So ultimately I would write down this A plus A dagger, A plus A dagger term, which is appearing over here. So this whole term which I have written as A lambda naught P naught is actually the statement of the whole A with the dipole approximation. Similarly, when I have written A P naught dagger, that is the whole integration with respect to with a delta function in between, which converts the integration over here into just sum of two terms. All those two terms I'm collectively writing over here. So there is one more term in principle which is made up of A lambda naught P naught and 1 plus iota kx e to the power I omega t. So I have just written it figuratively as of now. I'm not going to do computations with this. I'm just telling you, if I just open it up, do the dipole kind of approximation, I get various kinds of terms in the Hamiltonian. I have not written all the terms because in the realistic setting, which we are going to discuss later on, I will cleanly write all the Hamiltonian terms. But you can see an emergent structure which is present in the Hamiltonian over here. You see all the terms have a character that there are certain operators. There is an operator A which belongs to the quantum field, and then operator P which belongs to the atomic set. So there are mixing up of operators, some operators acting on the field states and some operator which act on the atomic states. So I have a two-party system now. One state which is the state of the atom. I have to write down the state of the atom, and then there is another part which is the state of the field itself. So this is two-party quantum system, and the operators of both of them appear as a product term in the Hamiltonian. Okay, that is the generic character in terms of a light matter interaction Hamiltonians, where you will see most of the times operators of this kind, interaction operators of this kind, which do appear in the game, and you will see that these interactions Hamiltonian would be useful in computing various quantities. We should just wrap up with the discussion of relativistic version of that, so that we are just comfortable with dealing with relativistic particles if needed. Most of the times we will be discussing only with non-relativistic particles. Nevertheless, let us go ahead and discuss the structure in terms of relativistic particles. So in the relativistic setting, the action has to be written in terms of a Lorentz invariant object, as we have discussed previously. And one of the most simplest Lorentz invariant object for particles can be written in the following terms. I write down the first term in terms of the total path covered by the particle. Momenta, mc, in some sense, some units of momenta, times the path covered, d tau. Remember, d tau square is minus eta mu nu dx mu dx mu. So this d tau is a square root of a minus eta mu nu dx mu dx mu, which is the path length. Then there is a term which is motion of a charged particle q in presence of a mu, and there is a coupling between the a mu and the velocity of the particle dx mu upon d tau. If I just forget about the second term for a moment, the first term is just the path length information. The dynamical quantity is path length. M and C are fundamental constants in some sense. Not fundamental, but constants. So only thing which changes along with the path is the path length. So if I just forget about the extra term, then if suppose I am talking about a free particle, not talking to any electromagnetic field, the second term will not be there, and the first term has to be extremized in order to obtain the equation of motion. So therefore, what will get extremized is the path length. So particles, free particles will move on the extremal path, the shortest path, the geodesics. So this is the geodesic motion part. The second term which I have now put in is just the force due to charged particle moving with velocity dx mu upon d tau in a vector potential a mu. Remember, this is just a natural generalization. I want to have a coupling between the velocity for vector and the a mu vector potential. This is the simplest scalar I can write out of that. A mu dx mu upon d tau. This is the local velocity at a time tau, let us say, and a mu is the vector for potential at that location. So this is a scalar overall, and I integrate it to accumulate all the scalars along its path. So now in presence of electromagnetic force, electromagnetic field, the charged particle does not move on a geodesic. It has to be corrected by this much of a force in some sense. So this is the Lorentz invariant interaction. That is how you write down any Lagrangian of the system which is consistent with the Lorentz symmetries. Now next what I do, I again write up the d tau in terms of square root of minus eta mu nu dx mu dx nu, and then I divide and multiply the whole term by d tau and d tau. So first this d tau has to be written as eta mu nu dx mu square root. Then I multiply and divide by d tau. So one d tau I leave outside and another 1 by d tau I sneak into the square root. And into the square root it becomes dx mu upon d tau and dx nu upon d tau. So therefore this becomes velocity 4 vectors. The second term I just leave it alone. I do not do anything to it. See what happens. In the interior of the square root, this contraction is there. Mu and nu are supposed to take all possible values. But remember, eta mu nu in Cartesian coordinate system can be written as a matrix whose only diagonal entries are non-zero. Minus 1, 1, 1, 1. Other thing, everything else is 0. So I will have only 4 terms surviving. The first half of that would be eta 0, 0, which is minus 1. So overall minus of eta 0, 0 is plus 1. And then dx 0 upon d tau, which is c square dt square upon d tau square. So that is just the eta 0, 0 term. The remaining 3 diagonal terms are the velocity, spatial velocity vector square, dx upon d tau whole square. So the whole term, the square root term, can be written in terms of these. Again, as before, I have left the interaction between the particle and the electromagnetic field as untouched. Now what I do in the next step, I pull out this c square dt upon d tau whole square. When I pull it out, I will get a c times dt upon d tau. One extra c I supply here, mc square will be there, and dt upon d tau, I cancel that d tau which is appearing here. So overall, the integration measure becomes dt. Since there is a dt upon d tau and already there was a d tau outside, those two d taus cancel each other. The same thing I can do on the second term, which was untouched till now. The derivative, which is d upon d tau, can be written as d upon dt times dt upon d tau as the chain rule. And again the same game, this d tau here and this d tau appearing over here can be cancelled out. So ultimately I have a Lagrangian which is minus mc square integration of dt square root of 1 minus v square upon c square and minus q dt integration times a mu dx mu. So this is the action, and the Lagrangian would be just minus mc square root of 1 minus v square upon c square minus q times integrand of this dt, a mu dx mu upon dt. Now note one fact, that in this game, here I have obtained the Newtonian velocity, not the Lorentz covariant velocity. Lorentz covariant velocity would have been dx mu upon d tau. This time I have obtained dx mu upon dt. Because of the chain rule, I replaced the derivative with respect to tau into derivative with respect to t. Similarly here, x dot here, when I pulled out the c squared dt square upon d tau square, the d tau got cancelled, and inside also I had a dx upon dt whole square divided by c square. So this x dot is also Newtonian velocity. So now I have a Lagrangian, which is Newtonian velocity written in terms of Newtonian velocity. X dot here is a Newtonian velocity magnitude, and x mu dot upon dt is dx mu upon dt is the Newtonian 4 velocity. dx0 upon dt will be 1. dxi upon dt will be the 3 components of the spatial velocities. Okay. So if once this Lagrangian is given to me, I will proceed ahead and I will write down the Euler-Lagrangian equation of motion. First, by taking the Lagrangian's partial derivative with respect to xi dot. Xi dot is sitting at two places. This v square upon c square, otherwise x dot square upon c square, is made up of x1 dot square plus x2 dot square plus x3 dot square upon c square. So xi dot square is sitting, xi dot is sitting here, as well as in this interaction term dx mu upon d tau dt is summed over for all mu's. So when I do the partial derivative with respect to xi dot, this square root term will undergo derivative, which will give me the first term, and the second term will survive only when xi dot will see the corresponding term with ai multiplication. So qai will be the second term which will be survived. What I have to do further for Euler-Lagrangian equation, I have to do a time derivative of this del L upon del xi dot. Do this. This is just a simple algebra you can do. You have to just see where is the time dependency in this term. Xi dot, x dot square, and ai, all these three functions are time dependent. M, C, and Q are not time dependent. So overall, this term will undergo time derivative, the square root will undergo a time derivative, and ai will undergo the time derivative, and you will get three types of terms. This is again a plain and simple algebra you should be able to do, and you can just write down the total derivative of del A upon dt in terms of partial derivative plus partial derivative with respect to position times dxj upon dt. So this is just the simple expansion of the partial derivative of ai with respect to t. A total derivative of ai with respect to t can be written in terms of two terms. So overall, this would be the left-hand side of the Euler-Lagrange equation. The right-hand side is just del L upon del xi. I will search in the Lagrangian where is the position dependency. First term in the Lagrangian has only velocity dependency, no position dependency. Only in the second term, through a mu, position dependency comes about. A mu dx mu upon dt, or a alpha x dot alpha, a mu x mu dot, whatever way you write. Then the partial derivative will just hit the a, because only spatial derivative of position can hit only the a, and I will get this term. What I have to do, I have to just equate the left hand side and the right hand side, and you will see I have this structure. Okay, where I have brought in the two terms of the left hand side. The last two terms of the left hand side are also thrown onto the last two terms of the left hand side are also thrown into the right hand side. So now you see the terms which are appearing on the right hand side have a peculiar structure in them. You can see I have a del ai upon dt here and del a0 del xi over here. These two terms I'm going to combine and write it like this over here. The remaining terms which comes with xj dot, here I have a xj dot and last term has a xj dot. The two terms also I combine and I get these two terms. And now you can realize that the two terms, one term which is independent of xi dot and another term which is dependent on xi dot or xj dot, they have a structure of Fi0 and Fij respectively. This is just the ijth component of the field strength tensor of electromagnetic theory, and this is just Fi0 component of the F mu nu. This gets multiplied with 1, which is u0. Remember, u0 was dt upon dt. This is Newtonian velocity, so that is why this is 1. And this is xj dot, which is a uj. So ultimately, you see the two terms are Fi0 u0 plus q times Fij uj. Collectively, it is Q times F I alpha U alpha, where alpha is being summed over 0 and 1, 2, 3. So this is the relativistic sort of force law for a relativistic particle which is moving along in presence of electromagnetic field. You see, this is almost like the non-relativistic term apart from an extra 1 minus v square upon c square to the power 3 by 2 term over here. So you see, this 1 minus x dot square upon c square term is an extra to the power 3 by 2 actually is an extra, but that's about it. You can just, if I ignore that term, I'm just in the non-relativistic limit whose equations of motion we had just seen. Okay, so now we can move forward and write down the effectively the Hamiltonian of the system. The conjugate momenta corresponding to xi is already available with us from the del L upon del xi dot term, which is this. What I'm going to do, I'm going to convert all the xi dots which are appearing in the Lagrangian in terms of their momenta. I just take this qai dot term on the left hand side, so I will be left with mxi dot upon square root term. What I do, this is ith component on the both side. I multiply one more pi plus qai on the left hand side. As a result, I will be multiplying mxi dot the square root quantity on the right hand side, and then I sum over all the i's. So left hand side will become the vector dot product between p plus qa, which is the magnitude square of the p plus qa vector, and the right hand side will become m square x dot square divided by 1 minus x dot square upon c square, which is fine. So I can take this m square c square as well. So you can see that I can divide by c square, multiply by c square in the numerator, and take m square c square on the left hand side. So I will be having p plus qa vector mod square divided by m square c square is equal to v square c square divided by 1 minus v square by c square. And now I can play a simple componendo dividendo kind of term. I add the numerator denominator on the top and leave the denominator in the bottom, and this is the structure I will get. I have written 1 minus a square root v square upon c square the whole square. This is just the funny way of writing 1 minus v square by c square. Why I am doing so, that will become clear in a minute. Now let us look at the Hamiltonian. The Hamiltonian is pi xi dot minus Lagrangian. Pi I already know is mxi dot divided by this square root factor minus qai. So Hamiltonian will be pi xi dot. So both the terms here and here will get multiplied with xi dot. These are the two terms, and this is the Lagrangian subtracted out. Now you see again, open it up. This is again simple algebra. You should do it as a homework exercise. You open it up, you will see three terms ai xi dot gets cancelled in the four terms here. So I have a mu x mu dot. This is a0 x0 dot, a1 x1 dot, a2 x2 dot, a3 x3 dot. Three of them get cancelled from the spatial portion coming from the first term here. I'm left only with qa naught term. Okay, and the remaining terms combine neatly into just this object, mc square divided by 1 minus x dot square c square. Let me erase it up so that things become very visible to us. So the remaining square root terms can be combined together. Out of potential terms, vector potential terms, many of the terms got cancelled. Only one term qa naught will survive. Qa naught with x0 dot in the Newtonian version is 1. And while the square root terms can be combined together, as you can see, and ultimately I will get mc square divided by 1 minus v square c square square root. You can identify this term as the E is equal to mc square expression, where the gamma factor is an extra. So this is how the typical E is equal to mc square is written. The m effective is m rest mass, proper mass, divided by this Lorentz factor. This is a free particles energy. In presence of electromagnetic fields interaction, what electromagnetic field does is to ascribe an extra energy part into the Hamiltonian, which is charged particle talking to the scalar potential A naught. And now you will realize why I had written this thing as a funny way, because square root 1 minus x dot square c square is description is needed for writing the Hamiltonian in terms of momenta. So square root of the whole quantity on the left is the quantity which is appearing over here. So you see my Hamiltonian is mc square times this Lorentz factor is just p plus qa whole square plus m square c square divided by m square c square to the power 1 by 2. So this is the Hamiltonian of a relativistic system, relativistic particle. But you can see the same term 1 by 2 square root 1 by 2 term can be written as 1 plus p plus qa upon m square c square. This denominator m square c square cancel this m square c square to get you 1, and the second term is p plus qa divided by mc whole square, and overall 1 by 2 factor, and qa naught term remains as it is. We have seen it before. Previously we had seen if no electromagnetic field was present, a naught was not there, a vector a was not there, then it was 1 plus p square upon m square c square 1 by 2. This is what the kinetic energy kind of expansion we had done before. This time the role of p is played by p plus qa. So you see, for small momenta, if rest mass is higher compared to the momenta, then I can Taylor expand this thing as we had done before as well. Previously I had obtained rest mass energy plus p square by 2m minus p4 upon 8 mq upon c square. This time also I am going to get those terms, but p replaced by p plus qa. So you see, it has very much similar kind of non-relativistic plus expansion, meaning non-relativistic term is just the first term, relativistic correction is this, and higher powers will come through the expansion of these terms. Only change is that p is replaced by p plus qa. Now you see the structure in relativistic setting as well, that if I open it these terms out, I will get various terms, p square and a square from the first term, but there is a p dot a and a dot p terms also. Remember again, these are individual operators when I go to quantum theory. So I would not write p dot a plus a dot p as twice p dot a or twice a dot p. I will just keep them along, p dot a plus a dot p. In the second term again, I have a p plus qa to the power 4. So I will have a p4 term and a4 term, and then there will be various kind of term, p cube and a, then pa, app, meaning all the factorizations of p and a together, they should add up to 4 powers. 3 powers of p and 1 power of a, 2 power of p, 2 powers of a, 1 power of p and 3 powers of a will be the cross terms. And they can be written in terms of as many forms as quantum mechanics allows them, meaning I would not club them as one term. I would get p to the power something and a to the power something, or pa, those kind of structure. But you see, in most of the systems which we have discussed and seen, the coupling terms have this structure that one operator belongs to the quantum mechanical set, p operator for instance here, and one another operator which is coming in the cross product belongs to the quantum field set, which is the a operator here. So ultimately, in light matter interaction, I would have a generic structure like that there will be, in the effective Hamiltonian or the perturbation Hamiltonian, will contain only structure such that two operators, one from field side and one from the quantum mechanical side, will be talking to each other. They will be cross product with each other, and those operators will hit the joint state of the field and the matter. I have now two-party quantum system, quantum atom and quantum field. They are joint operators. The coupling between them is through one operator from atom, one operator from field talking to each other, having cross product, and this perturbation Hamiltonian will evolve the state correspondingly, as we have seen. A more representative, illustrative strategy of dealing with that would be done in terms of Unruh DV detector, which in the next class we will see, where most simplistic but a very general setup would be considered, where one operator from atomic sector and one operator from field sector will be put together as a coupling Hamiltonian, and then we will take states and evolve with that perturbation Hamiltonian. So see where the states land up ultimately. So this is what we will do in the next class. I stop over here for today.